second talk for today, which is titled A Journey Towards Embedded Software Development. And the speaker for today is Nitish Davey. Before starting, I would like to give a brief introduction of Nitish. Nitish works as an application developer for MCUs at Microchip Technology. He has a rich experience of working in the multi-domain environments like medical and healthcare products, advanced driver assistance systems, etc. Particularly, he has significant exposure in developing camera and video technology for automotive industry and integrated development environment for microcontrollers. Having been fortunate enough to work on bare metal programming to more complex multi-core middleware applications, Nitish realizes the importance of building efficient and quality software for the product that he develops. Despite his expertise, he still considers himself to be a student in the expensive field of technology. He is also interested in the art of debugging and reverse engineering, which serves as his rescue tools when it comes to programming nightmares. So, over to you, Nitish.
Yeah, hi. Thanks, Ananta, for this brief introduction. Hope I'm audible enough. Mm,
Yes, you're audible.
Yeah, I have to apologize as I'm running on low bandwidth. Unfortunately, my network had some issues, so please pardon. I may not be able to share my video, but yeah, let's get started. As we heard the talk, the next title is A Journey Towards the Embedded System Application. Let me know once my screen is up. Okay.
It's
Is it
loading. Yeah,
okay?
it's visible now.
Okay, fine. Okay, so let's get started. So I just want to place a question before the audience. It's simple, like as you see, can you number the apples? Any this is it's an open question. There's no right or wrong answer to it. So feel free to take it.
Five.
Hmm. Yeah. So for us programmers, it starts with 4 because the way we programmers see is from zero because for us everything starts from zero and zero matters a lot. And as Ananta gave a brief introduction, my name is Nitish Davey and I work as a software developer in a company called Microchip, uh, where we are a semiconductor manufacturing industry. And yeah, my hobbies are like love, art and music, and that's pretty much about it. And as we go towards the embedded software development, let me briefly give an intro of the topics that we are going to see today. One is what is the branches of embedded software development. Again, we hear this the term embedded software development, and as any other field, even this is a kind of vast area where there are a lot of scope, different career opportunities that we have in the embedded software development. And we are going to look at the various branches of embedded software development, and then what are the skills that we need to become a good embedded software engineer. And thirdly, it will be the future of the embedded software market. And these are the three things that we will be going to look into today. So let's begin. And yeah, I would like to start with a story, and this is not something a cooked up story. Uh, Hope you are able to see my screen and follow too, as my bandwidth is low, so you might feel a lag, but please do bear as I take into each slide. So this is how it all started, and this was my final year project that we did, and the circuits look messy, the things are not in place, and we didn't worry about the presentation aspect, but we wanted to learn something out of what we had been educated since for the 4 years. And we took a simple project. So I'm not going into detail of what the project is, but this story would help you understand how it all started and what how it helps as what we have learned in our 4 years of college or the degree that we are doing. So I'm basically from an electrical and electronics background. So we chose a simple microcontroller project, and we chose a simple 8-bit microcontroller. And I believe many of you might have heard about these microcontrollers and microprocessor, you might have studied. And when we proposed our project, we were not so much welcomed, as we got some comments like these days we have an advanced processors and controller like 32-bit and all. So we are still, we got a feedback telling that we are still going into that whole 8-bit controllers. But then our target is to achieve something simply, something cost effective. So with that, we proceeded and we put into practice whatever we had learned. So this is how it all started, and all whatever the circuits that you are seeing here, nothing is like we didn't get a ready-made boards. We actually studied the circuits. We wanted to make them, and we used a general purpose breakout boards to make and test it out. And at one point, what we faced was when we were running out the project, there was a serious issue that the complete project was getting restarted. So there was a reset that was happening, and we couldn't understand. So now the problem lies, where is the issue, whether it is into the hardware or should we look into the software. So as Mr. Mahesh was explaining and giving a background about the hardware, for us as embedded engineers, both plays a very major role. We have to give concentration on both the hardware as well as the software part also. So here where the art of getting used to the hang of understanding the electronic circuits as plus the software that is acting on it comes into picture. We were trying to figure out, and we were trying to first try to reproduce where is the issue that's happening exactly, and we were able to isolate first in place. That was our first milestone, and then we were able to find a solution. So there are motors that were connected to this project, and if you are from an electrical background, you might know if there is a motor or a coil, and when it is like powered on and when it is switched off instantly, it will create a back EMF, which was causing the complete circuit to go for a toss. And the solution that we got at that time, as we have studied all the electronic components, was just put a small diode so that it doesn't conduct in the reverse way, and that solved our problem. So this is just a kind of example that I want to give it to relate how debugging slowly started from my initial years of my career, how we started out all with this, the things that we have learned, how it helped in our actual projects. So yeah, with that, I would like to get into this architecture of an embedded system. So here we see the at the bottom layer the hardware, where Mr. Mahesh gave an explanation of the various hardwares, and on top of which the embedded software engineers come into picture. So there are several layers above the hardware. The first and foremost is this device drivers, which directly interact with the device. And yeah, hope I'm audible and there is no lag. And if there are, if something is missing, please do pause me or raise hands. Yeah. So, and the next thing is the operating system, the yellow box that you see, which may or may not be present, and that depends on the application that one is trying to build. And next is the middleware, and the above is the top layer application. And this is a kind of simple, typical embedded system architecture that we used to get, we used to see in many of our devices. So with that, we'll see what are the branches of an embedded system software that we are going to look into. So as you see, we have networking, bare metal software, Linux, embedded Linux, and RTOS. So as far as I know, these comply into an embedded software product. If you take any of the product, you will be almost seeing one of them or the combination of them into that kind of product. And we may, as we go into each of them, we can try to relate to some kind of product where you are using maybe in a day-to-day life also. So going on with that, we'll look at the first. and foremost is the bare metal. So what does come into your mind when you call a bare metal? Any guesses? So it's nothing but what we directly write onto a simple device. So as you see, there is a tiny microcontroller that you have, and you are directly trying to write something into it, read something into it, and it always kind of deals with some small application. It could be just reading some temperature and just notifying. It could be just turning on a relay or something very simple as that. So those are like we are just trying to directly interact with the microcontroller registers, its peripherals, read the status, and then try to communicate with other peripherals as well. So if you could see, there is an example of what a bare metal coding was. How do we, when I say about bare metal, what it does look like. So say I have been given a microcontroller, and I'm taking an example of turning or blinking an LED. So the microcontroller's GPIO, or the input output pin we call, is connected to a LED, and I just want to do a blinking of it. So how would I go about it when I see a bare metal programmer? So this is kind of a simple application, but it's not limited to this. I'm just taking this as an example so that it makes sense out of it. So if you could see, there are something. I hope you are able to see my mouse cursor. There are certain registers that we are near to access, and we directly go to that registers and see what are things that we need to set. For that, we need a good understanding of the corresponding device. So in this case, say I have taken a particular microcontroller. You generally we would get a data sheet. We call it as a data sheet. As embedded engineers, we should be able to read through the data sheet, and we should understand the schematic. We should understand the registers that they are going to support, the peripherals that they are supporting, and the electrical characteristics. So before getting into actual code, so that would be the first step when you get a hardware. So you would go through, you would understand what all the hardware supports, what is the clock, maximum clock that the hardware can go, what is the power supply that we need to give, because these days the power supply is a kind of concern that has been coming. So we need to go through these electrical characteristics to understand, and then once we are done with it, we would be directly accessing those registers. And this is what I call bare metal programming. So you have been given some to create a simple application, and you have a controller, and you go just writing and reading of the registers, and you get your application done. The next comes the hardware abstraction layer. As the name itself stands out, there is something that we want to abstract. So say now the customers, when as a chip in manufacturing industry, the customer wants to use or create an application, so they may not want to go through all these hassles of reading out the registers and understanding of the status, and they may not want to really do it, and it actually slows down the market time to get the product out. So that is where there is another category comes in called hardware abstraction layer, or HAL. Today, many of the companies out of the box, they ship along with the chip the hardware abstraction layer software, and this is one layer above the bare metal software, or it is in a way that how the users are going to see or call a function. So to give a typical application of what an abstraction layer is, I would put in another picture here. So both the code on the left and the right are doing the same thing, but there is a distinction. So which one would you think is as more readable? Is it in the left or is it in the right?
I feel both are same.
Yeah, it is, both are same. In a way, both are same. That's what I'm reading. So both are same, but there is something more to it. So here, if you see on the left side, there are, for setting a pin, here it is directly dealing with the hardware names where port B and out set, and we are setting this particular pin. But here on the right side, the user has to call set underscore pin. That's the API, and the implementation of it. If you see the inclusion of the file, it tells avr hal.h. Now the avr hal.c would have the implementation of what is the set pin is going to do. So with this might look a very simple when we see from this kind of application, but if you see, there are other peripherals like UART or PWM wherein things really get complex. So for sending a data, we might need to query a lot of registers, like check the status and then put it into a buffer. So all those things come into play. So that is where we provide a hardware abstraction layer to the customer, so that they don't have to worry about this nitty-gritty details when they are kind of working on application. Their intention is to create an application, but not to focus and spend time on understanding the registers, right? So that is where the hardware abstraction layer comes into picture.
Hello, I have
Yeah,
a question. So,
yeah.
how this hardware abstraction layer is different from driver? I mean, is it one kind of driver, or what, how much difference lies between HAL and the driver files?
Yeah, so when we call a hardware abstraction layer, so that is where the abstract we try to abstract out the hardware details. So when we call a driver, say there is a UART driver, right? So there is I'll take an example of the UART module. Say the customer wants to go into and transfer some type of data over a UART. So now, as a driver programmer, what we would be doing is we would be taking care of writing into those registers, as I mentioned. So
Okay.
yeah, so it's the abstraction that we are going to give into the hardware, I mean this HAL layer, but the driver is nothing but what the internal hardware needs to be done. So say here on taking this example, we have a API called set underscore pin, but it actually requires the pin to be the hardware needs to know whether I should set a pin to an input or output, and then what is the value that I need to pass into it. So there are some details the hardware expects,
Okay.
and always the customer may not want to go into all those details because their intention is to create an application, right?
Right.
Yeah, so that is where the driver programming into comes into picture, and we part of my work involves like this. So we provide customers these kind of abstracted APIs so that they can use it. So there are complex peripherals that are in microcontrollers and microprocessors, and it is a kind of cumbersome job to do sit and go through data sheet and try to identify all the registers and then configure. So rather than what we the customers expect is you give some kind of abstracted layer. I don't want to understand or know what all things needs to be done. I want this job needs to be done. I want to transmit something, so I need to just send, okay, you are transmit. If I call you are transmit, it should do the job.
Okay. Thanks. Yeah.
Yeah, and on top of it is where the application development, as I told, using this controller, you can do many applications like blinking and LED is one application, but there could be other application. The controller could have ADC module or something else which senses time to time and then sends out some data, or like if you take a simple example of the air conditioner, it always tries to maintain the temperature, and how it does is it tries to sense the temperature. Once the temperature is sensed, the analog signal comes into the controller and we process on it and then try to display something and try to maintain or keep the compressor to have that same temperature. That is a kind of typical application that we do on top of these things. So that's yeah.
Uh, I have a question here. When it comes to any of these communication protocols, how do you deal with any kind of a fragmentation or drops that may occur in your communication between systems?
Okay, so
Be
you are
it B to C. So
sorry.
things like
uh,
when it comes to any of these protocols, be it SPI, UART, or I2C,
mhm.
at least in I2C you have like clock stretching, which
Yeah,
occurs with respect to master slave devices. So
yeah,
there are
correct.
like times where you have some form of an error in your transmitted data, or some form of packet fragmentation that would have taken place. So
Yeah,
how do
so
you address that?
Okay, so when it comes to the communication protocols, there is always a kind of handshaking mechanism that we do, right? So say you are using a UART communication program, and there is again in UART you have both synchronous and asynchronous, and it is as an application developer, it is my responsible to make sure that the data has come. So now the hardware itself will provide certain level of kind of integrity to what the data is. And say we have, if you take a UART, there is something called parity and all these things that comes into play where we can make use of and see the data that we have received is the one that is what is expected. And there are several other methods as well, like say there are methods like cyclic redundancy check, where we can incorporate those things to make sure that our data what we got is the expected one.
Okay, but I have a question again. So when it comes to parity checking, so the
Mhm.
parity is just one single bit. So if you have a corruption in the parity bit itself, your integrity is lost. So how do you overcome that kind of a scenario?
Yeah, so there will be NAC, right? So there's something called negative acknowledgement, and so that will basically mean that the sender should resend the, whatever the packet that was sent again, right? So there are some. It depends again on what protocol we are specifically looking into, right?
Yeah.
Yeah, maybe we can take up, I think.
Yeah, maybe we
During
can
the
take it at the end. So it depends on the communication protocols that we are using, and there are certain error checking mechanisms that are available. Like as you mentioned, there is in I2C, there are some bus collision mechanisms that are there. So there are apart from that, there are parity error checking mechanisms also there that are implemented at hardware level. So maybe we can go into those at the end if that's fine, as I'll move on to the other slides, and we can take those questions at the end.
Yeah, sure, sure.
Yeah, okay, thank you. Okay, yeah. So as I was talking about the bare metal programming, and the next branch is the embedded Linux software. And why is it so important with the Linux software is it's free. It's basically free, and it's an open source, and it has a great community support, and it actually kind of reduces the development time cost. Many of these boards today ship with a customized embedded Linux kernel. So this is a kind, maybe a kind of typical hardware that we have where we want some of these stacks that are already there. So we call it like there is a term, we don't want to reinvent the wheel. So there is already a OS that provides us with a basic file system and all the other functionalities, and that's where this Linux, this monolithic kernel comes into play. And the Linux goes well with many of the boards that have come these days. And here also again in Linux we have a Linux driver development, Linux kernel, where the heart of the OS is being customized. And one classic example that I can think of, and which is very popular, and any guesses on the Linux kernel that you know that has been modified and it's today popularly widely popular, like which is being used? So today almost everybody have smartphones, and the smartphone OS was revolutionized by this Android OS. And if we look at the framework, the base framework, it is a Linux kernel that's been modified. And if you see on top of it sits the hardware, which it's nothing but the SoC of the mobile processor, and it could be a Qualcomm's SoC or any other vendor's SoC, where the Linux is being ported. And top of it we have certain libraries, the native libraries which we want, since they are the native libraries that would compile. And there is this Android runtime on top of it which does the other jobs of managing. And this really has revolutionized the smartphone OS today. And it all started with modifying or customizing the Linux kernel and building on top of it. And that is one classic example of embedded Linux software, but there are many more to it. There are various flavors of Linux that are constantly going for modification, especially for servers. So there are OSs for small tiny embedded devices, like we have all these development boards. You might have heard about a board board called Raspberry Pi, BeagleBone, and Intel Galileo. These are the various hardware development boards that have a customized Linux OS into it. So all the names that you see here, Yocto, all these are like customized Linux kernels that have gone into these kind of development boards. So this is again another field where there is a huge scope for the embedded engineers to work upon. And again, you may choose to either go into a kernel development or driver development. So if you are particularly interested into getting into embedded Linux software, it is good that you would if you could understand the OS internals, OS architecture, the file system, the booting process of a Linux OS. All these things comes into picture. And yeah, that would really help you in going ahead with this embedded Linux software. Yeah, and the next thing is the RTOS. We might have heard about the real-time operating systems. Any examples or any guesses where you might have seen a real-time application system where you think that this could be an RTOS or going? And what do you understand by a real-time operating system? So anybody heard of RTOS as real-time operating systems? This term? So unlike the other OS, real-time operating systems are very critical, and they are supposed to act on the given particular time. So in other words, they are simply deterministic. So we can't miss out the events. And again, as we see, there are categories over here. We call it hard and soft real-time systems. So if something is missed in the hard real-time system, it's an error. So it is going to cause a serious, even a human loss. And if I can take a simple example, say today we have all these high-end cars. So if you could see inside a car, what all things are we getting in a car? It has a rear view collision. It is going to have an anti-locking braking system. Assume that if it fails, the car is supposed to apply that anti-locking braking system at particular instant, and if it fails, it could lead to a human loss, human life loss. So that's where this real-time operating system comes into play. So inside a car, there are ECUs that are keep on monitoring all the parameters with the sensors that they have been hooked into. And the moment they have this threshold reached, they are going to act upon it. So that's where we come with this deterministic things. And one thing about the RTOS is these, we call it schedulers. So how the schedulers have been designed into the RTOS plays a major role. And we have other applications also, like say multi-threading application. So today we talk about the multi-cores. I'm not sure if I think Mahesh might have explained about the multi-core processors. So earlier we used to have a single core which the system would take and process into many threads, but today we have these multi-cores in some architectures like ARM. So we have many processes where there are multi-cores, more than single core that is involved to achieve what we wanted and to be deterministic in terms of the application. And there are certain RTOSs, if you want to try out, say like free RTOS, which I had used on some boards, where you can try to play around on the message box queues and see how it works. So mainly on the IPC, we call it the inter-process communication, all these things. And yeah, this is one of the other field in the embedded software system where we have a huge scope, especially in the avionics. They mostly use this real-time systems, because that is like one system. So I read an article about the space missions that are going. So that is a critical software, because there is no return back of those software that you cannot debug, because once it's deployed, and everything has to be very deterministic. And so that is where each and everything of even the memory, even the temperature, everything comes into play. And choosing a good real-time operating system is very critical to such applications. So when when it comes to the real-time operating systems, I would say the understanding of the task management, the resource management, how it handles the interrupt, which is a very major role in the RTOS, where we set the priorities. All these things are very essential if you are interested into or pursuing in real-time operating system careers. And yeah, the last one is the networking software. So today we are almost surrounded with lots of devices where we connected, and network or communication is not just for humans, right? So it's even for the devices that we interact with. And one field of networking software where I can think of is IoT. You might have heard this term, Internet of Things, where everything is connected. Be it opening a car via wirelessly, you have these days called wireless car key, and to turning on and turning off your room light or fan, everything has connected to the cloud services, and through a mobile phone you try to connect, and that's where this networking software comes into play. And it's not just about the software and how secure that the software is, how reliable we have the software that is being written in the networking software. We do use wearables. Many of might have used these wearables in your wrist that monitors your blood pressure or other parameters. So it has to be, the data has to be transferred over to your mobile phone for your maybe kind of logging or maybe to further processing. So what all things that as a networking software we need to be aware is the stacks that we need to understand, especially on the Ethernet stack, the Wi-Fi, and the BLE, we call it Bluetooth low energy stacks. So all these things are very essential when we want to go into this networking software. I had an opportunity to work on the wearables where we wanted to monitor the pulse and kind of create an application in the mobile where the user gets the data, and that's where we had to work on this Bluetooth stack and the applications. And this is another kind of booming technology that is upcoming with all the connections, and most of the things are getting into cloud these days. So if you are really interested in this pursuing the networking software, I would recommend you to understand how the protocols. Here we have again, as we have a protocols for embedded system, there are certain protocols for IoT like MQTT, we call it MQTT. So all these things, so an understanding of basic networking system, how the network model is working, and maybe Wi-Fi and Bluetooth stack, it would really help in getting into this networking software. Okay, so coming to the skills, uh, so of all the branches that we have seen so far, there are certain basic skills. These are like kind of basements that we want to put. So when we as embedded engineers, it is really good if we have master over any one programming language, that would be a C and C++. So C++, since these days we are more going towards the object oriented, that's why I had mentioned C++. But almost all the embedded device deals with a basic low level language like C. And then definitely a good understanding of the electronics that would help you, because as I mentioned earlier, embedded software is not just about the software that you are writing. Sometimes you will have to work into the hardware. You will get an opportunity to work into the hardware where you will have to identify where the issue actually lies, so and what needs to be done. So a good understanding of the electronics and about the microcontrollers, the architecture, especially how the microcontroller is being architected, how the instructions are being processed, whether it is a pipeline. There are complex microcontrollers that have come, especially on the 32-bit side, and the architectures that they have brought in, like multi-stage and multi-pipeline system architectures have come into picture. So it's all that we start from a simple controller and then keep adding one layer above one layer above. As you get opportunities, or as you try to work on this, you will get more idea about all these things. And as I mentioned, basic understanding of an operating system would be good, as we have seen that RTOS and these embedded Linux OSs that are getting into some of the devices which the applications wants to use. So it would be good if you have this understanding of operating system. And then again, yeah, that's like a good debugging skill to use the oscilloscope and logic analysis, because as I think one of the point of the query that we got is how we understand if there is some signal that data is not transferred in a UART. So I've seen my colleagues use the oscilloscope and to check the signals and see where something has gone wrong, because there are times when we will have to really get our hands dirty into the hardware and see if we are not able to find it in the software. There could be some sort of hardware issues also that would be happening. It may not always be the software, but it could be the hardware, or it could be some temperature changes that are causing the issues. And we have actually seen such issues. Say if there is a ECU that's gone into the car and it has temperature beyond what is expected, and now the system is malfunctioning, and that's where we need to understand the electrical characteristics and understand all these debugging using the logic analyzers and the oscilloscope. And any version management software that I would leave just like optional, whichever you choose. It's just that as you code, you just keep your code into some either it could be a GitHub or some open source version managing software, so that you can retrieve it at later point of time. And most of the companies are now working on this version management software based approach. So that's about the skills part that we would I would recommend to really concentrate or work upon. And then the last is future demand. So I am really not a person of statistics or metrics, so I didn't choose to put any kind of statistics here, but I always go with what I like to work upon or what is my passion is. So if, as you have seen, there are a lot of divisions or a lot of streams that we have in embedded system, embedded software system. It is up to each and every individual in what they want to pursue. They could pursue in some product. It's finally about the product, right? It's finally about the need, and finally how we are solving the problem with our intuition and with what we have learned. So that's what my take is. So I really believe the future scope for the embedded software engineers is really good, and it's up to our imaginations. As we seen, the technologies keep doubling up. It would be the need for the hour is to write a good quality code that is scaling for all the applications, and with that we will able to achieve and solve most of the real-time problems that we have today. Yeah, and I just want to leave an end note with this quote that I love from Mr. APJ Abdul Kalam. He always tells, "Don't fear for facing failure in the first attempt, because even the successful math starts with zero only." And even for us embedded engineers, as I started, it all starts with that zero. And even I also started with zero. I was kind of completely unaware about programming, as I have from the electrical background. So then I started slowly learning a basic programming language, and then I tried to incorporate all those things what I've learned, and with that is what it helps. So face your failures and you will slowly overcome your fears. Thank you, and maybe we can go for any questions.
Please unmute yourself and ask your questions or post in the chat.
Okay.
Okay. Hi, Anupam here. I would like to ask this question to specifically Nitish sir. Like just now he mentioned he was from electrical background with zero experience. So same is the case with me. I'm just starting to like dwell in the domain of microcontrollers. So if you could share a short strategy or roadmap, it could be very beneficial.
Yeah, sure. So as as I mentioned, even I was from electrical background. So what I did was I found my interest in this embedded system. So the moment I identified, I got a small development board, we call. So as I've shown many development boards in my slide, right, like a Raspberry Pi, it may not be complex as what I've showed, but it could be a simple. There are controllers like 8-bit controllers which will help you. The main thing for us as embedded engineers is to go and work on those projects. So take any mini project, whatever you like to achieve, start with those projects, understand how the code is being converted. So as you write, so there are certain applications. So what I did was there is a simulator, I'm not currently able to recollect the name, which will help you to write code and see in real time what's happening with your code. So I use such tools for me to help, and then I got a small development board, and where I tried to program and flash and saw the outputs going small, get a small sensors, maybe try with some small sensors. They are very cheap, like a light sensor. So where you can try and understand about various peripherals. Embedded system is nothing but understanding about various peripherals and how they deal with the microcontroller, how the signals, how the power is acting. And programming is when you try to write small snippets of code to achieve this application. So in a nutshell, the brief, what I would say is have a small kind of development board, and even if you can't buy one right away, you can try to think of a kind of small application, and say you want to create a small calculator application. Just try to visualize the zero code of it and try to write and see. You don't need a hardware for writing a calculator application. You can open any editor, but then that application you can convert it into a small into embedded hardware, where you can play around with buttons. Say when you press twice, an LED could blink for the result that you want to see. So that's how I started, and slowly I learned with the development board, and I got a hang of how the programming and I mean kind of working into the embedded system.
Okay, sir. Just two small questions.
Yeah.
First is how to make a smooth transition from C programming to embedded C programming, and the second one is what are the specific profiles that the companies offer in India? Okay, thank you.
Okay, sorry, I didn't get the second question.
Second question was that what are the specific profiles that an embedded engineer can get into, both in
Oh,
software and hardware side?
okay. Okay, so for the first question, what you have asked is how to transition from C to embedded C. So it's just the terms that are being used interchangeably. Say when you call it an embedded C, it's just that the syntax and some of the hardware related registers that you're going to access. But if you are good at a C programming language, you don't have to worry about the embedded C part. It's just about getting a small board and play around with it. You should be fine, and you should be good enough to work with it. So there is nothing like embedded C and just a C. It's about the hardware that we are going to access. So I would say that's the reason I told you can take some calculator application, try to write it in C. You can come up with the algorithms, and the same thing you try to now visualize in a hardware, it becomes an embedded C. And for the second question, as what all the various roles is what you asked, right? Like what are the various roles that as embedded engineers the companies offer? So as a starter, you would be. It depends on the company that you are going into. So say if you are getting into a kind of electric vehicle company kind of thing. So there the profile could be they want you to write some applications for the power controlled and motor control applications, and so the designation wise it depends on the company. So how the company designates their candidates, but otherwise on a big scale, if you see, as an embedded engineer, you will be kind of getting to work into these bare metals. That's what the starting place is. Else you will be working on a layer called middleware, where you may not directly interact with the hardware, but the hardware abstraction layer above that, where the application is lying. So that's where you might be getting an opportunity. and that's where I also started. So I was not working on a direct bare metal at the start of my career. So I started with an application where I had to write an application inside an embedded device. So that's how it all started. Hope that answered your question.
Yes, sir. Yes, sir.
Yeah.
Thank you.
Yeah.
There are two questions in the chat. The first
Okay.
one is from Akhilesh. Would you recommend any specific video or lecture series regarding embedded electronics to learn from and practice?
Okay. When I started out, I used a site called All About Electronics. So it was a very nice site where it explained a lot of electronic concepts in a simple way. See, the fact was, coming out of a college grad, I didn't have much understanding on the electronic parts, kind of in-depth understanding. So as in you work on the products or the small applications, you will get to know. So the when you work on a small product, take a small embedded development board, and when you work on it, that's where you will get an understanding of the electronics. So apart from that, there are a site called NEPTL. It is from, I think, IIT, where they have I think open source electronics video course as well. And yeah, I think that's what I know, as far as I know.
And second question is from Ayushman. Can we
Yeah.
use Java for programming aspects of embedded software?
Java, what is it? Can you use Java? Okay, I'm seeing the chat. Java
Yeah,
for
for
programming.
programming aspects.
Yeah, so as I mentioned, the embedded software is not directly written on an Java layer. So as I mentioned, there is this Android application or Android SDK, right, where you are actually writing some application. Say you are writing a camera application, it is in a way kind of embedded. So you wanted to access a camera, but you are not actually directly dealing with the hardware, but the application layer, what you are writing could be in any language. It could be Java, JavaScript, or C hash, any high level language sorry, that you can write. But as for the embedded, I am not aware if there is any board that allows us to directly code into Java language. However, I remember there was one development board. uh, I am not sure about the name. I think it was allowing to code you in C hash.